So these kinds of levels of radiation are very, very extreme. But there are instances when people have received that level of radiation, and I wanted to talk about that as well, and give you a couple instances where people have received these very, very high levels of radiation. There were, when the atomic bombs were initially being tested, there were some incidents that occurred that involved very, very high levels of radiation. Mostly this would be neutron radiation that was received by people that were working with the bomb cores, subcritical masses. And there was one very dangerous series of experiments that were conducted during the shortly after the and actually before the Trinity tests were actually done. There were when scientists were experimenting to try to determine exactly what the critical mass was, they would take subcritical masses and they would put a couple subcritical masses near one another to try to determine by reading the amount of radiation that was actually being given off by these masses as they approach one another. They would try to determine at what point criticality would actually occur. And what they found was that with in some of these experiments, they were actually able to get some very, very good measurements, which enabled them to actually be able to construct the first atomic bomb. And there was one incident that occurred with a mass of something on the order of about it was somewhere around 6 kilogram plutonium mass. And this particular mass had gotten the name the demon mass because of this one particular incident that occurred in 1946, and then I'm sorry, it was in 1945 the first time that it happened. In 1945, there was experiments were being done with this particular mass, and I think it was in May, and there was one individual who was handling the mass, and I don't happen to recall his name right now, but he was working by himself, and he was using titanium carbide reflector to actually increase the amount of neutrons that were actually going to impinge upon that mass. And in doing so, he caused the mass very, very briefly to reach criticality, and it was determined that once he realized what had happened, he immediately separated. He actually, what he was doing was he was actually putting these, he was actually piling these titanium carbide reflectors around the mass, and he dropped one of the one of these reflectors. He actually dropped it right on top of the mass, and immediately this level of criticality was exceeded. And when he realized what had happened, he reached in and grabbed it and pulled it away, reducing the radiation. But he had already received something on the order of about 6 sieverts and died within, I think it was 29 days after his exposure. So despite this kind of an accident, it's very, very surprising. A lot of these people, I guess, that work with these things had sort of a callous attitude towards them, and they figured they could handle these things. They had worked with them for a long period of time, and they would handle them safely, or at least they thought it was safe. So there was another incident that occurred involving actually a Jewish physicist by the name of Louis Slotin. And Slotin had actually was someone who was very, very experienced in handling these materials, and he actually was someone who was actually involved in the assembly of the core that was used in the first blast, the Trinity blast at Alamogordo, New Mexico. So Slotin actually put that atomic bomb together, and after the war, they were still doing experimentation with these masses. And this particular mass, this demon mass, the one that had killed this other scientist a little more than a year prior to this second incident, there were 7 scientists who had assembled for this particular experiment. And it was done this time they were using beryllium as the reflective material, and there were two beryllium hemispheres that were supposed to surround the core. So they had placed the lower hemisphere and put the core on top of it, and then the idea was that they were going to see how close they could get with the upper hemisphere, and basically the only thing that separated contact between the upper hemisphere and the lower hemisphere was a screwdriver that was inserted between the two hemispheres. Well, what had happened was that apparently something happened. Slotin actually either the screwdriver slipped, and instantaneously the upper reflective beryllium mass came down on top of the plutonium, and just for probably a couple of seconds, criticality was reached. What people in the room observed was there was a flash of blue light, and Slotin actually reached in to grab this thing and pull it away, and there was a wave of heat that came over him, and he saw the flash and this wave of heat, and it was determined that by him doing what he did, he managed to save the lives of the other 6 people in the room, but he himself received a dose that was estimated to be around 21 sieverts, and he died shortly after that. I don't remember exactly how long he lived, but it was a very, very unfortunate accident. And there have been a number of kind of strange accidents that have occurred as well that I wanted to just briefly touch on. There was one that occurred in 1985. This had nothing to do with an atomic weapon, but actually was an accident that occurred because a radiotherapy institute in Guyana, Brazil, had moved to a new premises, and they had a cesium-137 teletherapy unit. So this was a unit that was capable of delivering 5 times 10 to the 13th becquerels with a dose rate of 4.5 grays per hour at a distance of 1 meter from the unit. And they actually left this unit in this building. It was a non-secured building. 2 men who were not authorized entered the building, and they were looking for scrap, and they found the unit, and they took it home and tried to dismantle it. And during the dismantling, the source capsule that had 93 grams of cesium-137 chloride in it ruptured, and all this stuff became dispersed. So the guys that actually handled it became contaminated with it, and then they took it to a junkyard, and the junkyard owner noticed after he bought it that it glowed in the dark, and he invited some of his friends over to watch this, and some of them even took small amounts of the radioactive material to their homes. So the upshot of this was that once people recognized what was going on, some of these people became quite sick. 249 individuals who were exposed developed various symptoms of radiation sickness, and they had to monitor more than 60 square kilometers of urban areas and 12,000 persons. 85 homes had significant contamination. 200 individuals were evacuated. 7 houses had to be demolished, and 4 individuals died receiving doses between 4.5 and 6 grays, but a lot of other people became very, very ill. There's another incident that occurred in Estonia, in Tamaku, Estonia, in 1984. 3 brothers entered a facility where there was radioactive waste, and they removed the metal container. Again, it was a non-secured facility, and they removed the metal container that contained a cesium-137 source. One of the men picked it up, put it in his pocket. It was a little pen-size cylinder, and he sold it for scrap metal. The man who took the source began to feel sick shortly after he took this, and a few hours later began to vomit. He had severe injuries to his leg and his hip, and he died 12 days later. The source was recovered at the man's home. This thing was really hot. At the source itself, not distance from the source, but actually handling this, he was receiving 2,000 to 3,000 grays per hour. So that would actually be getting a dose of just an absolutely enormous dose of radioactive material. And there have been a couple other incidents as well, which I'll probably have more to say about at a later time when we talk about X-rays, which is actually in the next chapter. But so there are, these are dangerous kinds of things, and what we can do to protect ourselves from very high levels of radioactivity. There's a number of things. We can shield against them. We can put distance between us and the object that's actually emitting the radiation. And the third thing that we can do is we can minimize the amount of contact time that we have. And these are the three things that we have to consider. Section 12.3 talks about risk, and they did a little study, which is shown on page 206, just showing that if you look at actual risks as they're listed by experts, that's people that are well versed in the field of risk assessment, versus this was actually a class of I think they were physics majors who were actually asked to rate the risk of certain activities. They did fairly well with some of the things, but there were many things that even these people who had actually had a course, were actually taking a course in nuclear physics, a course very much like what you're taking right now, and they rated the actual, in terms of rating how risky certain activities were, they rated some things much higher than they actually were, or lower than they were in some cases. So the class felt that X-rays rated 14 of the 29 ratings that they gave, rated 14 about mid-scale, whereas the experts said that they were much more dangerous than that. They rated them at a 7. Let's see, alcoholic beverages were rated by experts as the third riskiest activity, followed only by smoking and motor vehicles. And motor vehicles, which experts say are the riskiest activity, operating motor vehicles, that was rated number 4 by this group of the students. So basically, the book makes the point that familiarity breeds contempt. We all drive cars, so we don't think cars are all that dangerous. So we put motor vehicles down a little bit further on the list than they actually belong. And if you were to do this with the general public, they would tell you, they would probably rank nuclear power plants, or being near a nuclear power plant, even higher than 15. That is, when I say higher, I mean closer to 1. They would say it was much more dangerous than it's actually rated number 20 by experts. So lack of control creates fear. People rank nuclear power higher because they feel they've got no control over these things, and that but they have some familiarity with X-rays, because everybody's had an X-ray. Everyone's gone in and had dental X-rays. Everyone's gone in and had a variety of medical procedures. So people tend to be a little bit less worried about those kinds of things. And we saw, I think we've seen this before. It looked familiar to me, but you'll see that there's this little table in there that shows you dose on the x-axis and risk. Although I don't think it was shown as risk, but it's basically showing you linearity. And then we've got this region in here, which is just kind of surrounded like that. And this is that region where we start to see these stochastic kinds of effects, where we don't really know. We don't know that this actually goes linearly down to 0. So the question is, if we get very low doses, does our risk actually go to 0, or does it? Is this does this lose linearity at some point? And this is something that we don't really know. But we try to get something, we try to, when we're dealing with anything radiological, we practice, the acronym is ALARA, A-L-A-R-A, and it stands for as low as reasonably achievable. In other words, we do everything that we can to try to get these doses as low as we possibly can achieve. But we know that we're not going to get them all the way down to zero. So as I said before, we can lower exposure. The things that are most important are time. How much time do we spend near the source? We want to get as far away from this source as possible, because the amount of radiation that we receive is actually decreasing with the square of the distance. This is known as the inverse square law. The further away that we get, if we're at 10 times the distance that we were, let's say we got a certain dose at 1 meter, we go to 10 meters, we're going to be receiving only 1/100th of the dose. If we go to 100 meters, we're going to be receiving 1/10,000th of the dose. And if we went to 1,000 meters, we'd be at 1/1,000,000th of the dose. So the further away we can get from the source, the more rapidly that's going to fall off. We also have to consider shielding is another thing that's important. What can we put around the source that is actually going to prevent some of the radiation from reaching us? So we've got an example in your book, a little problem that they did. If the dose rate is 1 meter from a source, if the dose rate 1 meter from a source is 6.6 millisieverts per hour, what will the dose rate be at 4 meters from the source? So we can use these relationships. We take the dose in millisieverts per hour, multiply it by 1 over the square of the distance, and that's going to give us 6.6 millisieverts over the square of 4.0 meters per 1 meter. So that would be, comes out to be 0.41 millisieverts per hour.